All right. So we are now in lecture 32. Lecture 32. Okay. So this is just a bunch of needed results from complex analysis and an introduction to how to do things rigorously. Let's see. Is there a light switch for this side? I think this side is killing some of the recordings. No? Oh, well. All right. So what I want to do today is I want to give you a little bit of a sense of how you would make these calculations rigorous. So we've proved the central limit theorem. But the question is, are all the steps justifiable? And we showed some examples sometimes where the limit of the integral is not the integral of the limit. So here are two big results that you can prove in complex analysis. So the first is 20.5.3 in the book. Assume the moment generating functions mx and my exist for all t an absolute value less than delta for some delta greater than 0. So I want some neighborhood of the origin. Then the moment generating function of x equaling the moment generating function of y implies that the cumulative distribution functions are equal. And if the cumulative distribution functions are equal, since the densities are just the derivative, that means the densities are equal. The densities might be different on a set of measures 0. So what this means is I can change the value of my function in a couple of places, and it's not going to change the area under the curve. So if I have a continuous function that's a normal, all right, everybody can picture the normal density in your mind? Change the normal density so that whenever it is an integer, how old are you, Kayla? 7. The value of our new density is equal to 7 at every integer and is equal to the value of the normal everywhere else. Will this change the area under the curve? No. So I can change it at a couple of points with no real harm. So I should never be able to expect to get f of x equals f of y everywhere, unless I have an additional assumption. Maybe I want x and y to be continuous. If they have continuous densities, then I could potentially get something unique. But I've got to have the ability to change it at a small number of points. The second statement is essentially the same as the first. Assume I have a sequence of moment generating functions which converge for all t less than delta, which is greater than 0. Then there is a unique cumulative distribution function, f, which is given by the moments of mx of t. And whenever this cumulative distribution function is continuous, then the pointwise limit of the cumulative distribution functions of my random variables converges to the value of that cumulative distribution function at that point. This is basically the key result we need. We want to be able to say that if the moment generating functions converge, then the cumulative distribution functions go along for the ride, and they too converge. And if the cumulative distribution functions converge, then so do the densities. Okay? So that's roughly what goes on. And then we need to be very careful in stuff like this. So I want to write down two really bad densities. So the first is f1 of x is 1 over square root of 2 pi x squared e to the negative log squared of x divided by 2. And the second one is f2 of x is equal to f1 of x times 1 plus the sine of 2 pi log x. Okay, so here are two densities. If you plot them, they will look very different. Right? Are we surprised that these two densities look different? This factor here is highly oscillatory. What range is this going to go between? This whole bracketed factor. Where does it live? Yes? Between 0 and 2. And if you want, if it's between 0 and 2, maybe on average it's about 1. And so on average, it kind of balances out. Okay? So this is clearly non-negative. With a little bit of work, it does integrate to 1. Any idea how you might show that this integrates to 1? This does not look like a pleasant integral, or does it? How would you handle this integral? Eat a munchkin. Interesting. That's how we should handle the integral, by eating munchkins? Okay, no? Yes?
Well, maybe if you break... First of all, I'm going to want to get the 1 over square root of 2 pi. I don't want to...
The 1 over square root of 2 pi is is not going to really matter.
So like, I would break that up, and is it, I don't know, it feels, actually no, that doesn't work, sorry.
We don't know that many techniques. What techniques do we know?
Well, only X out, use substitution.
Yeah, use substitution. If you let u equal the log of x, then du is 1 over x. Oh, I have a 1 over square root of x squared. That's a 1 over x. This is screaming, do a u substitution. And when you do a u substitution, what distribution is this going to look like? A normal. So I believe this is called a log normal. All right. It's not that bad to integrate this once you see the u substitution trick. So these two distributions, do we agree they're very different? Okay, if you use complex analysis, you can calculate the moments. And they have the same moments at the integers. And so the moments are the following. E to the a squared over 2 plus e to the a minus 2I pi squared over 2, 1 minus e to the 4I a pi. Okay, so using complex analysis, I calculate these moments. So the way we would do it, we would do the expected value of e to the tx. I'm not going to go through the calculation. There's a strong suggestion that maybe we should do a change of variables. So we're using the fact, and I think we've talked about this before, that e to the I theta is cosine theta plus I sine theta. So if I take a to be an integer, what can you tell me about e to the 4I a pi if a is an integer? Yes? Well, it's complex, but what would it be? Let's say a equals 2. What's e to the 8I pi? It's just 1. So this factor would be 0, and you just get e to the a squared over 2. So and in fact, what if a was half an integer? What if a was, say, 7 halves? Then you would get e to the 4 times 7 halves. That'd be 14. It's still going to be an even number, and you're still going to get 1. So this factor is always going to vanish if a is a half integer. So it turns out that the moments of the first one and the second one agree whenever a is an integer or a half integer. So these two distributions, they have the same half integer moments. Which is extremely annoying because they're different distributions. Now, I'm not going to write down what the moments are of f1. I'll say that they are also equal to e to the a squared over 2 when a is an integer or half integer. But they differ for other values. And it's just because over here, this factor nicely vanishes. In general, you're going to have to worry about it. So you have this ridiculous situation where you have two different densities, but they have the same moments, and then they have the same half moments. It's not enough to show that they have the same densities. This is why probability, this is why real analysis is so hard. Because they're going to have the same moment generating functions. The moment generating function, it's a Taylor series expansion with the moments, right? If they have the same moments, they'll have the same moment generating function. So there's a result in complex analysis, and I just want to state the result, and then I think that's going to be it for complex. Let's say it's the following. Say x, well, we'll do complex. We usually use z for complex. Say zn converges to z, and say f of zn equals g of zn for all n. And I'll add f of z equals g of z, just to be extra safe. Then f equals g. And here, f is complex differentiable. So I just want to give you the barest outline of what's needed to make the subject rigorous. And I want to show you that complex analysis is completely different than what you would expect from real. So what we're saying is, imagine you have two functions that agree on a sequence of points that converge, and they agree in the limit. Then the functions are identical. Typically, you might say, imagine they have the same zeros. We'll look at the function h equals f minus g. And so if h equals f minus g, then h is 0 at all these points zn. And what it's then saying is, if you're 0 along a sequence of points that accumulate, that converge to a point, and you're complex differentiable, then you're identically 0. Let's think, is this true in real analysis? Can you give me a differentiable function in real analysis that is 0 at a sequence of points that converge, but is not identically 0? So real analysis, in some sense, is the subject of counterexamples. And eventually, you learn to just have a bunch of counterexamples. So how many of you have taken real analysis? OK. So can you give me an example of a function that is 0 at infinitely many points that accumulate? Say it accumulates at 0, but the function is not identically 0. I'm sorry? But it doesn't accumulate. So you're close, not the sine of x, but the sine of, I'm sorry? The sine of 1 over x. So let's let f of x, Kayla, what's your favorite number? I need a number. 6, good, 6 is large enough. Let's say it equals x to the 6th sine of 1 over x if x does not equal 0. And Kayla, what's your favorite number less than 1?
0.
OK, and we'll say it's 0. But you said 0 first, and 0 really helps me. Let's define our function like this. The only place where this definition is potentially bad is at 0. Right? Now, this function actually turns out to be differentiable. How would you prove this is differentiable? What would you have to do to take the derivative? But how would you actually calculate the derivative? Because I have a split definition. How do I do this? You have to use the limit definition. And because you have an x to the 6th, the sign is always between -1 and 1. So this is going to overpower. This will be differentiable a couple of times. And every time x is 1 over 2 pi, 1 over 4 pi, 1 over 6 pi, 1 over 8 pi, it's going to be 0. So this function has infinitely many zeros. They're accumulating. The function is differentiable, but it's not identically 0. So real analysis is a very, very different subject than complex analysis. A lot of bad things can happen. And essentially, this is what's lurking in the background, and this is what saves things. And you can see that this is basically giving us a uniqueness. If I agree on a sequence of points that accumulate, then I only have one possibility. There's only one thing I can be. Whereas in real analysis, I have many things I could be. So, again, this is not a course in complex analysis, but I want you to see what is necessary to make the central limit theorem work. That's what's really lurking in the background. And I'll post some notes on this for those of you who are interested. Always happy to chat more about this. Okay? I want to talk a little bit more now about just going through the algebra of dealing with these infinite sums. So for those of you who have not taken real analysis, how many of you are planning on taking real analysis? Okay, so this will definitely help those of you who are going to take real analysis someday. If you're not, it's still useful to get a sense of how you make these calculations rigorous. For a lot of things, we just need some rough estimation. And so what I want to do is I want to try to talk a little bit about how you would do some of these estimations. Okay, What random variable did we use last time? What did we use on Friday? Poisson. All right, so Poisson is a great one to use. Anybody remember the moment generating function of the Poisson? So x is Poisson with parameter lambda. The moment generating function of x is the expected value of e to the tx. And I think this was e to the lambda e to the t minus 1. Yes? This is the moment generating function of the Poisson. So there is a series expansion. And then the question is, can we say anything about how rapidly the moments are growing? So can anybody estimate the moments of this? We would have to take derivatives, oh God, and set the derivative and then set t equal to 0. So one of the big tools is to try to figure out how do you estimate, how do you get a ballpark sense for how big something is. I want the moment generating function to converge. So I want some idea of how large the moments are. Well, I'm going to be looking at the sum, n goes from 0 to infinity. Let's look at the expected value of x to the m. So I'll have n to the m, let's see, what is it? Lambda to the n, e to the minus lambda divided by n factorial. And I want to get some rough estimate for how big this is. So the first thing is, does this converge? So this is going back to sequences in series. You were supposed to have done this in 150. So how might we try to figure out if this converges? What could we use? We could use ratio test. What else could we use? You could use comparison as you'd have to find something to compare this to. So we can use ratio. Comparison would be a little bit harder. There's another test you could use. I think the ratio test is the easiest one to use. What else could we use? What's the other one? It also begins with an R. The root test, right? So let's try to use ratio. So when we use the ratio, we look at an plus 1 over an, right? So we would have n plus 1 to the m, lambda to the n plus 1, e to the minus lambda divided by n plus 1 factorial. And then we would divide this by n to the m, lambda to the n, e to the minus lambda over n factorial. Well, a lot of things cancel. The e to the minus lambdas cancel. The lambda to the n cancels with the lambda to the n up above. I have an n plus 1 to the m over n to the m. Right? So I'll have a 1 plus 1 over n to the m. And then I'm going to have a 1 over n plus 1. So what happens as n goes to infinity to this? I didn't mean to. Sorry. Thank you. So what happens as n gets very, very large? Yes. It's going to go to 0. At best, this quantity here is 2. So at best, this quantity is 2 to the m. Right? And then we have an n plus 1 down below. So this would be less than or equal to lambda 2 to the m over n plus 1, which is going to go to 0. So this will converge. In fact, it's good. Yes?
That's because m is a given constant.
M is fixed. Right. For each m, this is fixed. We could do a little bit more work and try to figure out how does this grow with m. And you'll get some sense of the size. But just using the ratio test tells us that this is going to converge. There will be a finite value. Okay? Now the next question is, how big is this finite value? Any thoughts? How might we try to figure out how large this is? What could we use? So we want to calculate how large this sum is. We've just shown that the sum converges, which is really not that surprising because we have a nice closed form series there. But I want to know roughly how big is the nth moment. It's finite. Kayla, would you be happy if I gave you some money? Do you care how much money I give you? No? Oh, okay. Here you go, 1 penny. You happy? You happy? Did you want more? Or was 1 penny sufficient? 1 penny was enough? Or you want more? Do you want to know how much I'm willing to give you? Yeah, okay. All right, so that's one data point, right? Wouldn't you like to know roughly how much this is, how big it is? How might we figure out how big this is? I want an estimate. We know it's finite. So, Caleb, do you know the symbol for infinity? Can you draw it? Okay, so come up here and draw an infinity right there. Okay? Right here. Good job. Excellent. All right, you can have a munchkin. All right, so it's less than infinity. We have a snow day. Can anybody get a bound better than infinity? And what do you think that bound should depend on? Okay, so one is we're probably going to use the geometric series test. What do you think the bound is going to be a function of? Yes.
M?
Probably a function of m. What else should it be a function of?
Lambda?
Probably a function of lambda, right? So my question is, can you give me an estimate for what this is as a function of m and lambda? And so what I want to do today is I just want to talk a little bit about how you would do calculations like this. How would you get a rough sense of what the size of a term like this is? This is a difficult calculation to do. The more times you see this, the easier it gets. Okay? We've just shown that it converges, so it's worth doing this question. But we'd like to do a little bit better than infinity. All right. Anybody have any thoughts as to what we could use to try to understand this? What could we use? Which part is causing trouble in this analysis? I'm sorry? Okay. I don't know anywhere I can really replace n to the m other than just n to the m.
Replace n factorial with square root?
Ah, so we could use Stirling's formula on n factorial. And that might give us a pretty good estimate. So because the n factorial is down below, do I want an upper bound or a lower bound for Stirling? Okay. I want a lower bound, right? So by Stirling, we know n factorial in the limit is n over e to the n square root of 2 pi n 1 plus small. If I drop the square root of 2 pi n, I claim that maybe n factorial is always greater than or equal to n over e to the n. For very large values, this is clearly going to be good, because I'm dropping a huge amount. And the square root of n is not going to change things enormously. I'm just trying to get a rough, quick answer. What about small values of n? If n equals 1, I've got 1 over e. Okay, that's good. If n equals 2, I've got 2 good. If n equals 3, I've got 6 over 3 over e, which should still be fine. I think something like this will be fine. So I believe something like this holds for all n. I've got to be a little bit careful. What could I do if this doesn't hold for all n? So a lot of times you have results that hold for all n sufficiently large, and there could be a couple of values in the beginning that are causing trouble. What should we do? Yes?
You would say for all n greater than or equal to whatever that n, the last n is where you use the word
So one thing is I could just handle the first few terms separately and just estimate what goes on for the first few terms. Another thing is I could probably divide this by a number that would then make it good, right? If there's a couple of terms in the beginning where the right-hand side is too large and then eventually it's good, well, maybe I just have to divide this by 100. And I would divide it by something independent of n, something to just fix what's going on in the beginning. I don't think we actually need anything. I think it's actually true for all values. But all this would do is it would just change our answer by a factor of 100. It wouldn't change it by something that depends on m. It wouldn't change it by something that depends on lambda. It's not going to change how it depends on the constants. Okay? And again, the purpose of today is to just give you a sense of how do you attack calculations like this. So this is always dangerous, but I will say I'm not going to give you anything like this on the final. Okay? The goal is for you to get a sense of how these things are done and to get a sense of do you want to continue in mathematics and see how these things are done. And if not, this is a great chance to put on the brakes. Okay? I want you to have a sense of what comes next. So let's say we have something like this. Then the term, n to the m, lambda to the n, does the e to the minus lambda really matter? Do I have to worry about the e to the minus lambda? No, that can just come in at the very end. I really just have to worry about this divided by n factorial. This will be less than or equal to, because when I take 1 over, I switch the order. So this will become an e over n to the n. Then I have a lambda to the n, so I can bring the lambda inside. And then I'll have a n to the m. So I have a bound. Right? Any thoughts on what I should do now? How I should handle this algebra? So, a huge part of mathematics is pattern recognition. What are the 3 things I know how to do? Add 0, multiply by 1, and take a log. And I was very glad that Kayla was not paying attention, did not yell out anything that could have been potentially embarrassing. Do you think we want to take logs, add 0, or multiply by 1? One possibility is take logs. My feeling is I'd probably want to do something other than take logs. Yeah, which one would I want to multiply by? Is there any similarity between this factor and this factor? They both have an n. What is this missing? What if I divide this by e lambda to the m and then multiply by e lambda to the m? Does it really hurt to multiply by an e lambda to the m? No. Right? That's something I can pull out because it has no n dependence. Right? By doing it like this, notice that this now looks like e lambda over n to the n minus mth power. Okay? There's a lot of stuff going on here. The goal is to just give you a rough sense of how you do calculations like this, how you get a rough order of magnitude answer for what's going on. Are we all okay up to here? Now what's this kind of looking like? What does it kind of look like? Yes? It kind of looks like a geometric series. But a geometric series has a fixed ratio. This does not have a fixed ratio. This ratio is getting smaller as n gets larger. Well, that should only help us. So eventually, if n is really large, what can you say about these terms? They're going to be really small. So one of the things we like to do is we like to break calculations up into different regions. And in different regions or different regimes, we can use different estimates. If n is small relative to e times lambda, this is going to be a large number raised to a large number. If n is large relative to e lambda, then this is going to be a very small number raised to a high power. So if I want to get a sense of what's going on, I would actually use this to break it up into different regions. And now you can begin to see where lambda is going to come into play. That's going to determine what is considered large or small. So again, I just want you to get a sense of how you would attack problems like this. So we have a sum, n goes from 0 to infinity. It'll be less than or equal to, and actually let me pull out all the different crap. We have an e to the minus lambda. We have an e lambda to the m. And then we have a sum, n goes from 0 to infinity, of e lambda over n to the n minus m. Right? So once n is really large, this is going to look like a geometric series, and we can bound with a geometric series. So large n bound with geometric series. So maybe this might be n such that n is greater than or equal to twice e lambda. Because once n is greater than or equal to twice e lambda, then this is going to be like a 1/2. Right? And then because I have a minus m, I might have a couple of terms in the beginning that are large, so it's probably going to be at most 2 to the m. So the sum is probably less than or equal to maybe 2 to the m plus 1. Something like that. If you want, I urge you to go through and do the calculations more carefully. But to just give you some sense, once n is really, really large, each of these terms is at most a half. If I were to sum a half plus a fourth plus an eighth plus a 16th, what would I get? Yes? It's just 1. So what if I summed 1 plus a half plus a fourth plus an eighth plus a... I would just get 2. But now it's going to be maybe a little bit larger, because maybe n is 0, and I would start off with 2 to the negative, with 1/2 to the negative m, which is 2 to the m. So I could have 2 to the m plus 2 to the m minus 1 plus 2 to the m minus 2, dot, 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 dot. So my feeling is probably something like this. If you want to be really safe, do m plus 4. That's going to be more than enough. It's going to overestimate, but it's going to be probably the right order of magnitude. So that handles the large values of n. So for small n, we have to figure out what's going on for small values of n. What's the largest this could be? So small values of n, what's the largest this quantity could be? Yeah, it's going to be at most e lambda, right? And then the question is, how far could the sum go? Well, it can't really go much larger than n greater than or equal to 2 e lambda. So you would probably get, each term is basically e lambda or less, bound by, we'll have another geometric sum, and it'll be, I think, like e lambda raised to, how large could n be? 2 e lambda plus 4, just to be safe. So probably something like that. And again, you really want to do this carefully. You want to go through it very slowly, but this would give us some kind of bound. And it would show us it's really growing maybe like 2 to the m, with a couple of constants and whatnot. But that would give you some sense as to how rapidly the moments of the Poisson grow. This is real overkill for this analysis. There's other ways of looking at this problem. But I wanted to do this you were supposed to have gone through Calc 3. If you hadn't taken Calc 3 here, you were supposed to have seen sequences in series and Taylor series. You were supposed to see convergence of series. There will be other math classes or stats classes that will require this. And that's why I thought this would be a really good time to have a digression on stuff like this. Okay? So we're not going to worry too much about analysis like this, but let's say we have that the mth moment is growing by at most 10 to the m. Okay? Let's see what would happen. So this is overkill. I think we have a much better result, but let's assume mth moment is less than or equal to 10 to the m. So if we look at the moment generating function at t, that's the sum, and it goes from 0 to infinity, and it'll be less than or equal to 10 to the m t, 10 to the n, t to the n over n factorial. For what values of t will this converge? So for what values of t will this converge? So one thing is if the absolute value of t is less than 1/10, it's terrible 10, it converges. Why? So it'll be comparison with a geometric series with ratio 10t, which is less than 1. So does everyone agree that this will converge if the absolute value of t is less than 1/10? So this is enough to show that it converges in some neighborhood of the origin. Can we do better? Okay, how can we do better?
Well, if you pick any fixed t, you have 10 to the n, and then you know n factorials eventually get bigger than 10t.
Right. So as was suggested, is if we just group the 10 and the t together, eventually n factorial is going to be larger than 10t. You could go through and you could use Stirling, you could use ratio, you could use root. It's going to converge for all t. Actually, converges for all t. But we actually only need this. So one of the things you want to be careful about is, depending on what you need, it's sometimes worthwhile not to prove the greatest result possible. If we just want to prove that it converges, the geometric series comparison was absolutely fine. We just needed some neighborhood. And the reason is, go back to the proof of the central limit theorem. Where did we evaluate the moment generating functions in the proof? So we evaluated them where? Yes.
At 0?
Not at 0, but at something going to 0. Where did we evaluate in the proof of the moment generating, in the proof of the central limit theorem? So what was the point we evaluated? Because remember, we had to standardize our random variable. So we looked at Zn was x1 plus xn minus n times the mean divided by what? What did we divide it by? Standard deviation square root of n. Right? So what we're doing is we're quickly reviewing our proof of the central limit theorem. The expected value of x1 plus xn is just n times the mean. And because they're independent, the variance of a sum is the sum of the variances, so the variance is n sigma squared, so the standard deviation is sigma square root of n. Right? And so when we calculated the moment generating function of Zn of t, we eventually got something like e to the negative, I think it was like mu t over sigma, and I think there was a square root of n up top, maybe mu square root of n divided by sigma t. I think this is what we had. And then we had the moment generating function of x evaluated at t over sigma square root of n raised to the nth power. You know, if memory serves, this is what we got when we used our formula for the moment generating function of this linear combination becomes this product. And so we're really evaluating the moment generating function near 0, which is great because that's where we're going to have the best chance of having things happen that'll be nice. And this is why, you know, those beautiful theorems from complex analysis that have now been erased, they always talk about a small neighborhood near the origin. We need the moment generating functions to exist in a small neighborhood about the origin. And so now we are evaluating this at t over sigma root n. As n gets very, very, very large, this is getting really close. And so when you look at what's happening with our sum, we actually have powers of n. But remember, for each fixed n, this is a fixed point, and then we have an infinite sum. So then we have to go through the analysis and show that the sum of the tail is negligible. And that's what we were basically doing. Is I said, look, we're going to ignore all the terms that are third order and higher. And basically they just are negligible, because they're all going to have a 1 over square root of n after we multiply by n and take the logs. Hopefully now you have a little bit of better sense as to how you would roll up your sleeves and do this calculation. Do you have a better idea, Kayla? You do? No, not at all. Not even useful at all, right? Okay, sorry. She tries to keep me grounded at times. She doesn't always succeed. Right? So this is how you would do calculations like this. This is the stuff that is needed to make the subject rigorous. Any questions about this? There are a couple of things that you should see once in life and only once. For those of you who've taken real analysis, have you seen the construction of the reals from the rationals and the integers using Dedekind cuts? You do that once and then that's it. Right? This is something similar. You want to get a sense of how do you make these arguments careful and rigorous. What are the dangers? In this class, have we done the danger of interchanging orders of integration? Have I given you an example where it doesn't work? We did that example? Excellent. The double sum? So you've got to be careful. Things that seem reasonable are not always reasonable. They're not always something you can do. All right. So this finishes off the main unit. Let me just turn off the recording.